Hello everybody, this is our lecture for chapter 10 about the gas laws. Again, to review what's going to happen, you're going to go through these notes. You should print out your lecture notes the same way you would for the regular lecture and fill in spaces where we're writing things. And in particular, you want to highlight for yourself the questions that you have, things that you would normally ask in class. And then I'm actually going to collect these lecture notes, so you're going to get 5 points just for taking notes. All right, this is one mechanism I'm going to use to make sure that you actually look at these notes, because these are going to be things that are going to come up on the test and your final as well. All right, and then also there's going to be an online quiz that is due before next class, or not next class, but rather next Wednesday's class. So that'll be 12/6/17. Okay. All right, so first our introduction to gases. We need to understand what gases are and why people were interested in studying them anyway. This started in the early 1800s. Initially, of course, gases are mostly invisible. So, you know, it's something we kind of just ignored. We took it for granted that it was just some sort of matter. Some people called it the ether, actually, which is also a chemical, so it's confusing. But it refers to the idea that there's some sort of other space and we just don't understand how it works. And so that's where they were coming from in the 1800s, until people started to be able to use chemical reactions to generate gases and capture them, and they started doing stuff like weighing it. And there's one guy who would do nothing but inhale it, so it's really weird. By the way, that's a bad idea. He actually had to hire a nurse to come and revive him because he suffocated himself several times. So, you know, not a great way of doing science. We no longer inhale the gases we make. But, so, first off, they had to figure out what is a gas. All right, and you can think about this question in a couple different levels. You could think about things on the particulate level, the particle level. On the particle level, they're, you know, molecules or atoms or elements, whatever, that are widely separated. Oops, missed an E. Meaning that there's a lot of empty space in gases. Wow, my E disappeared. That was weird. All right. So when you picture a gas on the particle level, it's something, you know, here's our container. The gas fills up the whole container. But the particles are spread out in kind of a random arrangement. There's no particular logic to it. Okay? And they take up the whole container. So this has to have a lid, otherwise all the gas would just leave. So that's the particle level image of what a gas is. On the macro scale, that is, you know, the larger view of the world, we're looking essentially at a substance that completely fills a space. So you can also think of it as has an undefined shape, because the shape of a gas actually comes from the container. It also has an undefined volume, meaning whatever the volume of the container is going to be the volume of the gas at that moment. And then of course on the macro level we can also measure pressure to quantify some aspect about the gas. And so effectively pressure is if I put a little gauge on my box here and I measure how many times these molecules collide and how hard they collide, that's basically what pressure is. So the official scientific definition is that pressure is the force exerted, now I have an extra E, on the container by a gas. Actually, by a fluid, to be technically correct, right? Because you can have water pressure as well. Fluids mean gas or liquid, so anything that flows is a fluid. So that you can have pressure of a liquid as well. That's related, because it's force, it's related to speed. So in this chapter we talk quite a bit about kinetic energy and how it is integrated with pressure. We have about 4 major units of pressure, and so they're all listed here. And this is an important kind of conversion table to have, right? These two words mean the same thing. We talked about this in lab, that millimeters of mercury and torr are the same thing. It's named for Torricelli, who invented the barometer. And to this day, we still use barometers. I think it was invented in like the 1600s, so it's been around a while. But basically, you have a pool of mercury here, and the tube is a super thin straw that has all the air removed from it, so it's a vacuum. And when you put the straw into the pool of mercury, what's going to happen is the air pushing down on the pool is going to force some of the mercury up into the straw. If I push a little bit harder, it's going to force the column of mercury higher, so higher pressure. So when we say millimeters of mercury, or torr, that literally is the height from the pool up to the top of the column. And it turns out that normal atmospheric pressure is something around 760 torr. So you can say down here that the conversion between atmospheres and torr, there's 1 atmosphere, which is average sea level pressure. But pressure changes on a day-to-day basis depending on the weather. And so this is sort of an average over a long period of time. So 1 atmosphere is average atmospheric pressure, and it is equal to 760 torr. So in other words, exactly 760 millimeters of mercury from here to here. And that's really tall. So you can recall from our Duma experiment in lab that the column of mercury is like 3 or 4 feet tall. Okay. And I don't know, by the way, why it's not centimeters instead of millimeters. There is another another measurement that you sometimes see. It's inches of mercury. It's relatively uncommon, but in the weather reporting, occasionally you hear that. Pascals are technically the SI unit of pressure, so that's the internationally agreed, like, basic unit. SI units of pressure, this is funny. A Pascal is equivalent to newtons per meter squared, which is also equivalent. So Newton means that there's a relationship here. So it's equivalent to kilograms per meter times second squared. So it's force per square area. Okay, and that makes sense because it's a container is the square area portion, and this is the force. So that's kind of the definition of what pressure is. As it turns out, pascals are a really small number. It's 101.325 kPa, which stands for kilopascals, kilo. So of course you can use what you know about the metric system to convert that into pascals. There's 1,000 pascals for every kilopascal. So Pascal units are really small. You almost never see them used as pascals. You generally see them used as in terms of kPa, and then you have to convert to pascals in order to get to your newtons and stuff. We're not going to do a lot of these kinds of conversions, but because nobody told me the direct connection between pascals and our basic SI units like kilograms, meters, and seconds, until I was way far into physics, I'm giving you this information free of charge because it's going to help you, okay? Many of you are going to need to go into physics next semester, and so it's important to realize that the Pascal is the SI unit of pressure because it's related to the other basic units, kilograms, meters, and seconds, okay? So there you go. Finally, in America, we have this weird one, pounds per square inch. This is what your tires say. So when you go measure your tire pressure on your car, like for example, my van says 36 psi. That's supposed to be what I fill my tires up to. If I'm at 36, the gas mileage is better, the car runs more efficiently, and it's good. Also safer handling. Okay, so that means pounds in a square inch. So it's an American unit because that's pounds. It turns out there's around 15 pounds per square inch in an atmosphere. Okay, so these are all conversion factors. That means I can use dimensional analysis to go from one to the other. So for example, if I had a car breakdown due to a flat tire in Canada, I could not use PSI. Maybe I could use atmospheres. So if I converted it to atmospheres, I want to put PSI on the bottom, atmospheres on the top. So essentially what we see here is that most car tires tend to be inflated about twice the pressure of air. In my car's case, it's a little bit higher than that. It's 2.4 ATM. Okay, we canceled PSI, so it goes away. So this is a handy set of conversions to have for your homework and so forth. Okay, so Boyle is the first guy to investigate gases that we're going to look at. These should all be reviewed from high school, so I'm just going to go over them kind of briefly. All right, but Boyles Law is about looking at volume and pressure, and this has to assume temperature is constant. All right, so if we look at the simulation here, this is a PhET simulation, so that we can see particle level pictures. It's telling me rather bossy here. It's telling me that I should pump the handle, so we're going to put in some gas molecules. And actually, in this case, I want 100 of them, so I'm just going to put in the number 100 over here. So there, we have 100 heavy atoms of some sort. These are gases, so they're going to fill up the entire container. We're a little bit above room temperature, but it's pretty close. So right now our pressure starts at about 0.55. Okay, so on your lecture notes, I want you to jot down a hypothesis about what's going to happen if I increase the volume of the box. Okay, I'm going to assume that you did that. So here's our little guy. He's going to make our box bigger. Maybe go a little bit bigger. Okay. We got to wait a sec because it doesn't happen instantaneously, but we see that we went from 0.5 to about 0.35. Okay. So we started at about 0.5 ATM and we went down by increasing the box size a little bit to about 0.35 atmospheres. So the conclusion from that, hopefully your hypothesis matched, but if not, that's okay. Your conclusion is that as the volume increased, pressure, we use P for pressure, pressure decreases. So these are inverse or proportional? I want you to tell me, proportional or inverse. Circle which one you think it is. All right, so again, hypothesis here. By the way, feel free to pause the video if you need to write stuff down. What's going to happen if I decrease the volume? So if I make the box smaller right now, if I squish things, what happens to the pressure? Okay. So here a good hypothesis might be that the pressure is going to increase. It's going to, see if we're decreasing volume. I guess if this is opposite like that, it's going to increase. So when I visualize this, I'm thinking like, you know, if I have a small car, everybody's kind of crammed in there. Or if I have a minivan, everybody's got lots of room. So it's kind of that kind of relationship. Oh, wow. So we made it so small that the lid broke. It just broke the container. Let's try that again. And actually reset the whole thing. So we end up with the same size we started with. So with 100 atoms of heavy material, we should end up with, I think we had a pressure about 0.5, right? Yeah, it's looking something like that. All right, so let's try this again. Make it smaller. Pressure certainly climbs, right? So 0.5 to, 5.5, it looks like maybe. So that seems to be true. My hypothesis is supported. Doesn't make it right, okay? So the hypothesis is supported because what I saw is as the volume went down, the pressure had to increase. All right, so tell me, yeah, again, proportional or inverse? Those are math terms I want you to be able to use. So we can plot this as a graph, okay? And so it turns out if I plot volume on the y and pressure on the x, and I measure the volume at a bunch of different pressures, what we get is this inversely exponential function, okay? Now, in science, we really like linear lines because you can utilize the equation for a line, and it's pretty easy to correlate, the data in the picture with that. So, in order to do that, we have to invert our pressure. This tells us that, hopefully you picked this on the last slide, the volume and the pressure are inverse of each other. In other words, as volume increased, pressure went down, right? Volume is higher, pressure is lower. Okay, so we can plot this for a bunch of different gases, and as it turns out, we get exactly the same slope for all these different gases. So your slope here, and that's kind of weird. All right, so V is on the Y, and the X is 1 over P, and our intercept here is just 0. So this is the format you're more accustomed to seeing, but there's no intercept. So we call this K here. It's a constant, and it doesn't matter what the gas is. It doesn't matter how big or the volume or the pressure are. This slope is universal, which is really rare at that time in our history of science. We didn't have that many things that were, well, consistent. And then Charles comes along and he says, I'm really interested in what happens with temperature. So in the prior simulation, in this simulation, we're assuming temperature stays constant. Oh, by the way, there's one more cool thing that this will show you. All right, let's take a look at this. So right now, let's make our container just a bit bigger. We have around, 3 atmospheres-ish. If I add, hey, we lost 2 particles. That was weird. If I add some lighter particles, it might not let me. That's weird. There we go. So the red ones are lighter particles, so they're showing that by having a smaller molecular size. And as we know for the Medulla lab, size is equivalent to size of particle, right? So the higher the molar mass, the lower the molar mass, the smaller the particle is going to be. So when we're looking at this, I'm gonna cool it down a little bit so we can see this better. It's pretty hot right now. Okay, closer to room temperature. The heavier particles move more slowly, and the smaller particles move very quickly. Okay, so here's another hypothesis. Gravity is turned off right now, so we're in space. If I turn gravity on, what do you think is going to happen? Pause the video and take a second. Jot that down in your notes here. All right, so I'm turning gravity on. Did what you think would happen? The light particles are still occupying the entire container, but the heavy particles have sunk to the bottom. So molar mass is also proportional to density. That's the Duma experiment, in short. All right, so the heavier the thing is, the more it sinks when gravity is turned on. Okay, all right, so Boyle was looking at pressure and volume, and Charles is looking at volume and temperature. All right, so in Boyle's law, what we sort of skipped over is the fact that the temperature has to be constant. Charles' law, we're changing temperature, so that means pressure is constant. Okay. All right, so we're going to watch this video by an MIT graduate student who clearly had quite a bit of time on their hands. There is circus music that goes along with it if you really want to watch it on your own. You can just go into the lecture notes and click on the picture. Liquid nitrogen is extremely cold. So to give you an indication, liquid nitrogen freezes at negative 321 degrees Fahrenheit, which is about negative 200 Celsius. So it's really, really, really cold. All right, and so that's what we're looking at here. All right. So he's got this beaker of liquid nitrogen and some balloon animals. I'm really grateful they labeled them for us because this looks like a snake, not a swan, but okay. So the swan's going in first. All right. right? So he's putting it into the really cold fluid, and it seems like the balloons are getting smaller. You'll notice he's wearing these bright orange gloves. The reason for that is they're super insulated because liquid nitrogen can damage your skin quite a bit. It's the same stuff they use in a doctor's office to kill warts and other viral lesions like that, right? Basically, you're just freezing them. All right, and then, so he put it into cold liquid and it got smaller. And he takes it out, so that means temperature's going up. And they return to their original volume. Okay, so Boyles Law studies that relationship. Oh, that one's cool. You guys should check that out. That guy's really funny. Like in a dry British kind of way. So what we saw was initially that he put the animals into the liquid nitrogen, so the volume decreased, they shrank, they all fit into this tiny little jar when the temperature went down. Okay, and then when he took them out, the temperature went up, it was warming back up, and the volume went back up. So these go in the same direction. Is that proportional or inverse? Of course it's proportional. Okay, so that means you can make a proportion out of it, volume divided by temperature, and it turns out the answer you're going to get when you do that for different volumes and different temperatures, it is always K, the same K as Boyles Law discovered. So here our slope is K. This does have an intercept though, and it's weird because the intercept is this negative number. It's really cold, negative 273 degrees Celsius, and it kept coming up, different gases, different experiments, different experimenters, and we kept getting the same intercept and the same slope. This is really the thing that intrigued scientists because it's crazy. You don't see that kind of consistency usually. Two other players in this game, Gay-Lussac and Avogadro. Basically, Gay-Lussac was a French guy who wanted to fly as high as he possibly could, and actually did manage to maintain the record until planes were invented. So in order to get the balloon to go as high as possible, he had to learn to manipulate gases. And you have to use different proportions of different kinds of gases to get the right density at different phases of the atmosphere. So he actually went up something like, I think, 33,000 feet, which is pretty high. It's about as high as most modern commercial aircraft go. And so in the process of learning to manipulate gases so he could be the best hot air balloon guy, he figured out that if you have a particular temperature and volume, the volume of a gas, regardless of what it is equal. So like in other words, if I have carbon dioxide and water vapor at the same temperature and pressure, these two volumes will be the same. Also, if you break them down, it turns out, say I capture all the hydrogen, all the oxygen from H2O, they're going to break down into a proportional numbers. So in other words, 2 parts of hydrogen are going to always pair up with 1 part of oxygen. So 2 liters of hydrogen, 1 liter of oxygen. And when that happens, when they react, when they mix together, you get H2O. Okay. So Avogadro's law, if you will, no one ever calls it a law, but Avogadro's relationship is about, he didn't actually invent the mole. That was assigned to him way after he was dead. What he did do was he counted, how many atoms do you have of gas in this sample at 0 degrees. And basically he eventually was able to conclude that if you are under standard conditions for a gas, which is 0 degrees Celsius, 1 atmosphere, 1 mole. So this is our standard temperature and pressure for a gas. It's different than for thermodynamics. Thermodynamics was 25 degrees. So keep that distinction in mind. STP for a gas, as it turns out, if you have 1 mole of gas, you have 22.4 liters. It doesn't matter what the gas is. It doesn't matter where you get it from. It doesn't matter what the molecular size is. None of that matters. All right? So this is actually 2 conversion factors that we can use. This will simplify your life if you understand what this is fundamentally talking about. i.e. if I'm at 0 degrees and 1 atmosphere of pressure, I can use this as a conversion factor. I do not need to use any of these other equations. I just convert from volume to moles. So that's a handy thing. All right, so the 3 laws that we typically think about being involved here is they all relate volume, all right? And so this symbol is proportional to. So volume is proportional to the inverse of pressure, so they're inversely proportional. Volume is proportional to temperature, and volume is proportional to moles. This is moles of gas. That's what N stands for. All right, well, since those are all true, my proportionality got moved. Since these are all true, we can put them together. 1 over P, T is on top, and N is on top. So you can say that volume is proportional to N times T divided by P. Well, nobody likes dealing with proportionalities because there's all kinds of special rules. So in order to figure out how to turn that into an equal sign, we employ that constant we kept running into. We called it K on other pages, but it's the slope of the line from Charles' Law and Boyles' Law. And so we have different units for that variable. We now call it R. I have no idea why, but it's called the ideal gas constant. Okay, so if we multiply by the ideal gas constant here, we can take away the proportionality constant and they become equal. In this class, we're going to be using this version of the ideal gas law. Next semester, we're going to be doing calculations about energy with it. So you'll use that or the calories. And then in physics, sometimes we need to have a relationship that relates to newtons, which is pascals. And then there's one for torr also. Actually, if you Wikipedia this, if you put in ideal gas constant value, you'll get like 50 or 60 different versions of it. The one we use is the one that has liters and atmospheres. One thing to notice is they all have Kelvin. So that tells us something important about the temperature. Oops. So now we can write the volume equals R times N times T divided by P. Now, a lot of people don't like fractions. So sometimes this law gets converted into... One of my students once told me that they think of this as pervert. Okay. But pressure times volume equals the moles of gas times the ideal gas constant times temperature. This is the fundamental unifying equation that explains an extremely large number of phenomena we observe, both with gases and with other fluids. So we call it the ideal gas equation. Ideal is an important caveat. We put it right in the name of the equation because it means that the gas has to behave in a certain manner. Okay, we're going to get into the parameters of that. By the way, if you don't remember from high school, you can use Boyles' Law to determine, I don't know why that keeps happening, to determine initial pressure and final pressure or something like this. It's kind of like your dilution equation. Charles' Law equation is inverse. Okay. And nobody really ever solves Avogadro's law separately. It's usually within the context of the ideal gas law. Okay. So these are equations that you can utilize as well, depending on the information that you're given in the question. You can always use the ideal gas law. Sometimes you have to do it a couple of times, like maybe you solve for moles once, and then you change the conditions and plug in for moles and solve for something different. But you can always use the ideal gas law as well. So this says to calculate the molar volume of oxygen at standard temperature and pressure. So molar means 1 mole. We're searching for volume. It's O2. And STP has special meaning. I have to know this for the test, okay? So you've got to know that it means 0 degrees Celsius, which is the same as saying 273.15 K. And it means exactly 1 atmosphere of pressure. So I can use the ideal gas law. 1 atmosphere times the volume, I don't know what it is yet, oops, I mixed up my constants. Wait, I take this back. It's 0.08206. See? 0.08206, or 0.0821 sometimes people round. Depends on how many sig figs I have. So that's R. And my temperature has to cancel with the Kelvin in the R equation. So that means I've got to convert it. I've got to use the 273. Now, sig figs are a little hazy here because we don't have any actual measurements of anything. Okay, but one thing that's important is you need to write all of your units. If you get lazy and you try not to write your units, you will calculate things incorrectly. So moles cancels, Kelvin cancels. We're going to divide by atmospheres because I got to get the V all by itself. And that leaves us with liters, which is a volume. Okay, so it's basically 0.08206 times 273. And you get 22.4147 from the calculator. That's Avogadro's law. So this is a proof that if you have 1 mole at standard temperature and pressure, it's going to equal 22.4 liters. Okay, so you can use that as a conversion factor, or you can solve for it. This obviously, PD equals nRT, is going to take a little bit longer than using this as a conversion factor. All right, well, let's try the same thing, but at room temperature. So the temperature here is going to be 25 degrees Celsius plus 273. I could use the 0.15, but I don't need to because I don't have any decimal places on this measurement. It's going to be 298 Kelvin. So that's what we called standard temperature for thermodynamics. All right, and so the pressure is still going to be 1 atmosphere. And I know you guys are going to be tempted while you're doing these problems to not write your units, but trust me, I've done these thousands of times, and if I don't write the units, I'm likely to screw it up as well. So you need to get in the habit of having the units. We're going to assume it's still 1 atmosphere. It doesn't say otherwise. That's why I'm assuming that. So what we end up with is 0.08206 times 298. And that says 24.45. So 1 mole occupies 24.45 at room temperature, and at 0 Celsius under standard conditions is 22.4. So that's a pretty big difference, 3 liters, just by increasing it by 25 degrees. All right, I want you guys to use the ideal gas law to do this one. This is going to be part of the 5 points I'm giving you for doing this, so make sure that you do that. You can pause the video. All right, so if we take the ideal gas equation and we move the V over, and we're going to move the R over, so we're going to divide by RT on both sides. Oh, I put V, I meant V down here. Sorry about that. Now what's interesting is we have mass and volume, number of moles and volume. Moles and volume is the same as molarity, right? Because it's moles per liter. So you can have, like, quote unquote, the molarity of a gas, even though it's not a solution, it's not dissolved in anything. It is spread out through a whole container though. Now, if we take this and we multiply both sides by molecular mass, just for fun, this is going to be grams per mole, right? Okay, I'm going to erase this molarity so I got some space here. It's not literally molarity. We usually use molarity in terms of solutions, and this is not a mixture. It's a pure gas. So anyway, but it's kind of like molarity because it's the same unit. We multiply both sides by the molar mass because it's hard to measure moles. So if we do that, we cancel the moles and we get grams per volume on this side. Well, as it turns out, that's pretty easy to measure in the lab. To measure the mass of a gas isn't that hard. You got to trap it, but you guys did that in lab. And we can determine the volume of a gas. That's a little bit harder, but we can do it. This allows us to figure out the molar mass. So you could even, if you wanted, you can write molar mass all by itself. So we could leave the P, the R, and the T on the other side. And so if we do that, you get this equation. And you can also, of course, as we did in the lab, substitute this for the density of the gas, right? So the mass per volume is density. So we can use the ideal gas law to find the molar mass of a gas, which is exactly what we did in the lab for the Duma experiment. Or conversely, if I know the molar mass, I could figure out the density of the gas using this equation, right? So you could solve for density as well. And that's basically the first equation we started with, right? So the density is the stuff on this side, the right. I moved it over to the left here, just for convenience. But it equals the molar mass times the pressure divided by the ideal gas law and T. Ideal gas equation, constant. So we can calculate a theoretical density of a gas, which is a valuable thing to know, because if you know whether the gas is more dense or less dense than air, then you know whether it's going to float or sink, which could be important if you're making toxic gases. You don't want them to sink and collect in the room that you're in, for example. This is an important thing. So we can calculate the density of a gas such as methane. Methane has an atomic mass of 12.01 for the carbon, plus 1.01 times 4, so that's going to give us 16.05. That's grams per mole, right? So I can use this equation to find the density, the green one. Density equals molar mass times the pressure. Our pressure here is in torr, and I know my R isn't in torr, so I'm going to convert that using that formula sheet that we made earlier. So it's going to be a little bit more than 1 atmosphere. It's 1.0, let's call it 1.03. We have 2 sig figs in our temperature, so that's going to be what limits us here. So I'm going to put that in. And this whole thing is divided by R. Times the temperature. So our temperature is 19 degrees. So I need that to be in Kelvin in order to cancel. So it's 292. So we're going to put that there. Before you bother to whip out your calculator with these things, you should really cancel your units, all right? And we would expect the density is going to be grams per liter for a gas. So atmospheres cancels, moles cancels, Kelvin cancels. So we get grams on the top, liters on the bottom, all right? So if we solve this equation, we'll know the density of methane. And it turns out it is 0.6899 and a bunch of other stuff. I only really have about 2 sig figs, so I guess what we would do is go. Grams per liter is just fine for a gas. They're very small, so if we did grams per milliliter, it would be 0.00069, which is kind of annoying. So we just use it in liters instead of milliliters. Now the question is that more dense or less dense than air? I don't know. I don't know the density of air, so let's go to the internet. We could figure out based on the composition of air, 80% into all of that, but oh, look at that. It looks like our density of air, well, that's grams per milliliter, so this is actually equivalent to grams per liter if you convert kilograms and meters cubed. So it's about 1.225 grams per milliliter. 1.225 grams per milliliter. So air is much denser than natural gas, which means the natural gas is going to float on top of the air. This means that I won't suffocate if I'm making natural gas in my apartment, for example. I mean, if your whole house was sealed up, eventually it will fill up, but probably it's just going to leak out through the attic. So that's good news. Not that you should make methane at home. It's difficult and expensive. All right, so we can do the molecular mass. That's the second equation here, the red one, right? So our derived equation here is the same one that we use in the lab. So if I have a gas where I don't know what it is, I could figure it out. All right, so for example, if we measure something at STP and it has a density of around 0.840 grams per liter, what is the molar mass? Okay, so that's one example, a question that we might have. And so I just plug everything in. You don't have to memorize the ideal gas constant. I give it to you. You have to know which one to choose, I suppose. I give you both the one with joules and the one without. Our temperature is 273 because it's STP. Then we gotta divide this whole thing by the volume. Oh, well, not really, because it's integrated into the density already. So I actually don't have to do that separately. Yeah, so see here, it's part of the density here, G versus P, but I do need to divide by pressure. I forgot to put that in. Okay. There. So density has volume in it. I didn't do grams separate, so I don't have to do volume separate, but we do need to include the pressure. And the pressure, of course, at STP is 1 atmosphere. Even though I know it's not going to change the math, I still have to put it because my units better cancel. Okay, so we get liters to cancel, and we get grams per mole. That's molar mass, right? So if I had this gas with a density of 0.84, it would have a molar mass around 18.82, it looks like. Now, looking at the periodic table, it's kind of handy to know how many atoms are in your unknown. We don't know that from this data, but if I assumed it was 1 atom, I guess the closest one would be neon, which has a molar mass of 20. Fluorine looks like it's close. It's 18.9984 on the periodic table. However, we have to remember that fluorine is a diatomic element. So the weight of that is actually going to be closer to like 38 grams per mole. Okay. So I wouldn't pick that one. So I guess probably this unknown gas was neon. There's error in these measurements, in your measurements of density especially. So it's probably not going to match perfectly. We just sort of have to get the best, closest answer we can. All right, so I want you to do this problem. One little tip, it tells you it's a diatomic gas. Okay, so you're going to use the same equation to do this. Pause the video and go ahead and take a second to do that. All right, so we come up to Dalton's Law of partial pressures. It describes exactly what it is. What it says is if you have a mixture of gases, the ideal gas law applies to each individual gas. So say this is like oxygen, and this one is like nitrogen, and this one is carbon dioxide, and so this whole mixture is air. The total pressure, P total, of air is due to the number of moles of oxygen, nitrogen, and carbon dioxide, all of those added up. So basically N means total moles of gas. It doesn't matter what gases they are. Okay, so we're just adding all the different N's up to get our total mole of gas, and that's going to give us the total pressure. Okay, so that makes some sense. So under standard conditions or normal laboratory conditions, the pressure here depends on the amount of gas particles. It's directly related to that. The more gas particles we have, the more pressure we have. Okay. Now, this is not an X. This is chi. It's a Greek symbol. What we use it for here is for a mole fraction. So like you can have a mole fraction of O2, and in air it would be 20% out of 100, so 20 out of 100. That's your mole fraction, which is the same thing as 0.2, right? So about 20% of air is oxygen, so that's what a mole fraction is used for. It's just the number. You could, if you had 100 moles total, you would have 20 moles of oxygen. That's all this means. You can use a mole fraction to determine the pressure due to just the gas you want. So in other words, if our atmospheric pressure is 760 torr, we can figure out the pressure due to oxygen using this relationship. So the pressure due to oxygen is going to be equal to its chi value, the mole fraction, times the pressure. And of course the answer to this is going to be in torr, because that's what my pressure is in. So it turns out that at atmospheric pressure we have about 152 torr of O2. Okay. That's what you're breathing. Now we can figure out the mole fraction. All right, and so here's the strategy to do this. We have the chi values actually provided here. When it says 30%, that's the same thing as saying for every 30 moles, I have 100 moles total of nitrogen. The other one's 24 out of 100 for O2. And hydrogen mixture here is 46 out of 100. These are all diatomic, so I do want to remember that, okay? We can figure out the partial pressure of each gas, but they don't give us a total pressure, so I guess we have to find the total pressure. Okay? They do tell us it's 2.1 kilograms and that there's a 5-liter container. So 2.1 kilograms is the total mass. I can also figure out what fraction of that mass is due to each one of these things by using the chi value, right? So here our chi value is going to equal 0.3, here is 0.24. So basically it's taking the percent and just turning it into a decimal value. So I could figure out how much of this 2.1 kilograms is due to nitrogen by multiplying by 0.3. So we get 0.63 kilos. I'm going to guess that we might have to convert that into grams. Then we got to remember there's 1,000 grams in 1 kilogram. So that's going to be 630 grams. Okay, we got to do the same thing for the O2 and the H2. Okay, this will give us grams of that stuff. From there, okay, we got a few more units to convert. I'm going to open up a new window so we have a little more room. You can do this on scrap paper if you'd like to. All right, so let's see, we said there's 630 grams of O2, I believe is what we just said. There's 46% H2, which means my chi value is 0.46, so it's going to be 2.1 kilograms times 0.46. Now you could convert out of kilograms at this point. It doesn't matter if you do it before or after you figure out what proportion everything is. Okay, so 0.966 kilograms here, and as always we show our conversions. I don't know why that one has an extra mark. Okay, so 966 grams of H2. Okay, so I'm going to just add that up here. Okay. Let's see. Okay, I had to copy everything over to a new slide because the black screen thing was being very laggy and erasing everything. So here we go. So the chi value for hydrogen is 0.46. Oh, the 630 is nitrogen, by the way. And so I can multiply by the chi value to get the proportion of the mass due to H2, and then I convert to grams per kilogram. So I do that all in one step here. For the last one, I'm going to do, let's see, O2. So the chi value for O2 is 0.24. And so we take the total weight times the fraction that's due to oxygen. I'm also going to do this conversion here. Now the next step is going to be to use molar mass to go from grams to moles, right? Because that's how I can figure out the proportion in using Dalton's law. The molar mass of oxygen, O2, is 32. Oh, wait, hang on. I don't want to do grams on top because I have grams on top here. I just noticed that they need to be on opposite sides. So the 32 grams is going to go on the bottom of the fraction. Okay, so we're going to put 1 mole on top. That's going to get us what we want. It's 32.00, but I'm being lazy here because it's hard to write on the computer. We can cancel a bunch of units. Kilograms cancels. Grams cancels. The fraction is not it doesn't have a unit, it's just a fraction, so it's sort of like a percent, there's no unit. And we end up with moles, right? So as it turns out, there's 15.75. We're talking about O2 here. So 15.75. So we only really have 2 significant figures from this data because it's 2.1 kilograms. So I guess I'll just round at this point. Keep 1 extra. There's that many moles. I do the same thing for the H2, right? So the molar mass, I'm going to take this number, divide by 2.02, and we're going to get 478 grams. Sorry, not grams, 478 moles. And then we can do moles of the, what do we got? We did H2, now we got to do nitrogen. So we have 630 grams of nitrogen. The molar mass of nitrogen is about 28. Because it's 14.01 times 2, so we get 22.5 moles. So this is the total, the number of moles that we have. Okay. The next thing we said we had to do is convert some units, so I'm just going to go ahead and do this up in the top where I got a little bit of space here. So we got 5 liters, that's the correct unit. Basically this 2.1, we're converting that into moles, so that was a conversion as well. 5 liters is correct, so my volume is 5 liters. Well, that's a V. I did not mean to put a V there. Try that again. So 5 liters here. We got the percentages used already, so you probably don't need them here. The temperature is 25, so now I have to convert that by adding 273, so we get 298 Kelvin. I am paying attention to significant figures as I go along. When I add its place value, so I'm making sure to have a 1's place in the answer. Alright, so now we can do our equation. So basically, we can figure the partial pressure of each thing, say, I don't know, the nitrogen first, by taking, so our equation is PV equals nRT. I take the moles, so for nitrogen, it's 22.5. So, and R is going to be this one. My T is 298 for all of them. They're all the same temperature, and I have to divide by the volume, PV, so I got to divide by V. So the pressure of the nitrogen is going to be 22.5 times 0.08206 times 298. Divided by 5. So I get 110 atmospheres. I know it's atmospheres because we get liters cancel, moles cancel, and oops, I canceled the wrong thing. That's a Kelvin, not a liter. That's Kelvin. Here's my liters. So I get atmospheres out of that. Alright, so plug it in and do the same thing for oxygen and hydrogen. Okay. And as a bonus question, you can add them all up to get the total pressure. Okay, so pause the video and go ahead and finish that. That is graded as well. All right, so the reason we care about partial pressure, there's a couple of things. If you want to weld something, the temperature of the flame matters a great deal. You've got to have it just hot enough to heat it up in the way you want. You don't want your weld to cool down too much, too quickly, so you got to have the right temperatures. And you control that by having the right mixture of acetylene and oxygen. Sometimes you want to use other gases that burn differently than acetylene does, so you can do that. There's different types of welding. If you're a diver, you care a great deal about partial pressure because the depth and temperature of the water will dictate what kind of mixture you need. If you're going really, really, really deep, they give you something that's mostly oxygen, for example. You need to have a higher pressure of oxygen for that to work. Or maybe it's the other way around. Maybe if it's a really shallow dive, they give you more oxygen. I can't remember. If we have any divers in the class, you can clarify for us. But the pressure and temperature of the water that you're diving in is going to dictate which mixture you use. Okay? It's not just putting air into a tank, because if you did that, you'd suffocate. That would be bad. Okay. Also, if you've ever had a spinal tap, not the band, but like the medical procedure, one of the things that they're measuring is how much oxygen compared to CO2 is in your blood, and that can indicate whether you have a spinal infection. And then, of course, they have to culture it to tell what kind of bugs might be in there. I think that meningitis can be diagnosed in this way. Also, there's a whole discipline called hazardous material handling, hazmat. Often fire departments handle this, and so they have devices that measure the partial pressure of different gases that might be hazardous. So say that there's like a bleach spill somewhere. They'll go in with their hazmat suit, big yellow bunny suit we call it, and they'll have devices that measure the pressure of chlorine and of other hazardous materials. And this way you know the level that's safe to breathe and what's not safe to breathe, and it helps them figure out when they can take their suit off. Also helps them figure out when the mess is cleaned up. Okay. All right, so the crux of gases is the assumptions, we said, the thing that makes them ideal, right? I referred to that earlier, is that they follow 5 rules. Okay, there's 5 rules. There were 4. I fixed it. The first one is that gases are a large number of particles in completely random motion. In other words, they don't flow together like liquids do. And they're not stuck together like solids are. The atoms need to be way smaller than the container, okay? Otherwise, we have issues. So like if the simulation we looked at were real, those atoms are way too big. They would not obey the kinetic molecular theory in that case. Atoms need to have lots and lots of space around them to behave as ideal. If not, they're too close together and neighboring atoms start to interact. Either they repel each other or they attract each other, and that has to be avoided in order for gases to be ideal. All right. We're also assuming that atoms don't occupy space, that the entire space provided inside of a container is taken up essentially by nothing, which is weird. But if we had something in there, then the gas would interact with it, and that would not follow predictable rules. Okay. So that's related to number 3. We can't have any attractive or repulsive forces. Okay, so anyway, number 3 is about related to number 2 insofar as we don't want to have attractive or repulsive forces between the molecules, because if we did, they would sort of stick to each other or bounce off more rapidly. That means that basically momentum is just conserved. When these 2 atoms or molecules run into each other, we want momentum to be conserved. Rather than having like one of them stick to the other one. Well, momentum would still be conserved then, but basically the particles are going to have the same average energy between the 2 of them that they had in the beginning versus the end. You wouldn't want attractive or repulsive forces to interfere with that, because then it doesn't behave as an ideal gas anymore. Finally, or not finally, but number 4, you can transfer energy between the molecules. So in other words, if we have like one molecule running really fast and one of them going really slow, when they collide, the slower one is going to move faster and the faster moving one is going to move a little bit slower. The energy is the same, overall. It's just a matter of which particle has a larger proportion of it at the end. When we talk about the energy of a gas, we're talking about the average kinetic energy. So in other words, if you count the amount of energy for each and every particle in the sample, it always has a distribution. So assuming that the temperature is constant, you might have a distribution like this. So this is the population on the y-axis, and the energy, or the kinetic energy, the speed even, on the x, right? So most of the particles have this energy, but there are a small portion that have even higher and a small portion that's really low. All right, never zero, but low. This, by the way, is called a Boltzmann distribution because it was invented by a guy named Boltzmann. Interestingly, if our temperature changes, if we have, like, say, I don't know, a cooler temperature, then the distribution changes. You have more particles with less energy. If it's cold, right? So our average kinetic energy is lower. So energy goes down if temperature goes down. And so that's intuitive, that makes sense to us. But what is a little less intuitive is the idea that individual particles are going to have different energy levels. And we have certain populations that are on average going to be higher or lower than the average kinetic energy. And so that's the way that all samples work. At any rate, when they collide, energy is transferred between them, but they're not sticking to each other and they're not repelled by each other, because if they were, it wouldn't be a complete energy transfer. All right, finally, our average kinetic energy is proportional to absolute temperature, which is 0 Kelvin. Is absolute 0, that's the lowest it can go. So what this is saying, not okay, that's 0 Kelvin. All right, so what this is saying is your average kinetic energy increases in proportion to the temperature. Okay, we can't actually get to 0 Kelvin, but if we did, it would mean we have 0 energy. Okay. By the way, absolute 0 was secretly referred to in Charles' Law graph when it said the intercept was negative 273 degrees Celsius. That's absolute 0. Right? And again, it doesn't matter what gases you test, you get that same intercept every time, which is strange. Okay, so those are our 5 assumptions. Some of them are flawed more than others are, but those are the things that make a gas ideal. So when we're looking at this chart, if a gas behaves as an ideal gas, it follows this dotted line on this graph. We're comparing pressure on the x-axis to this term here, which is basically like kind of an analog of the ideal gas equation. It's really kind of thinking about this as moles, so we could even just write moles here, really. So like as moles increases, we get farther and farther from the ideal gas line. And so the question is, which of these gases is the most ideal? CO2 is really far from the line, so not that. In the beginning, nitrogen at lower pressures, nitrogen's pretty close to the line, but it quickly deviates. So that if we're at, like, say, atmospheric, well, no, atmospheric is down here, I'm sorry. This is atmospheres, not torr. But, you know, if we're at like 600 atmospheres of pressure, nitrogen is really, really far from the line. So it depends which temperature you're at, but in general, the one that follows the trend the best is hydrogen. Hydrogen gas is the most linear relationship here, which means it is the most ideal gas out of this list. Okay. The reason for that is that hydrogen is the simplest gas, right? You just have one proton and one pair of electrons here in the middle being shared by 2 protons. That's what's happening in a hydrogen, so it's the simplest thing. So when 2 hydrogen molecules collide, there's no chance of like any distortion of the electron clouds, because all of the electrons are involved in the bond. They're between the 2 nuclei, so they're inaccessible. Whereas in other things like, say, O2, you have electrons that are outside of the bond, which means oxygen is going to have some kind of repulsive force. When another oxygen runs into it, you're going to have these electrons in the way, right? So this is going to be a repulsion in between these 2 things. So that means that, you know, oxygen doesn't behave as an ideal gas either. Okay. Nitrogen has the same problem. 2 unpaired electrons collide, they're gonna be repelling each other. So they definitely have repulsive forces. The other thing to think about is this one here. So number 3 is the big one here, where the attractive and repulsive forces are never actually 0. Hydrogen is the one that gets the closest. The other thing is number 2. right? The volume of a gas is very small. Well, that's true for hydrogen. Hydrogen's pretty small. But when we start talking about larger particle sizes, so the molar mass of this is 28, this is 16. I think this is, what, 44. So that's pretty heavy. That's probably why it goes down so sharply right here, right? So hydrogen has the smallest particle size, which means it behaves the most ideal, okay? So the reason we see these deviations is that point number 2 is probably not true. The bigger the particle size, the more this is in effect. Also, number 3 is unlikely to be true as well. Any unpaired electrons, any electrons not in the bonds, are capable of causing repulsion, for example, and maybe even causing attraction. We're going to learn in the next chapter about intermolecular forces that hold liquids together, let's say. So if you have too many attractive forces, then it won't even be a gas at all. Okay. So these are things that cause deviation from the ideal with increasing pressure. The best place to be, by the way, is right around this box. This is where the gases all kind of stay close to the line. So low pressure is a good place to be. That's where things are ideal. 1 atmosphere, for example, that's pretty low pressure. It's atmospheric pressure, but it's pretty low in the grand scheme of things. This goes all the way up to 1,000 atmospheres. So low pressure is better because that gives the molecules more space to run around, so that number 2 isn't as big of a deal. Also, it means number 1 is true. Lots of random motion if we got lots of space and lots of energy to move around. Okay. If things are moving quickly, the attractive and repulsive forces are less of an influence. So that means if temperature is high, then we have ideal gas conditions. So in a perfect world, to be an ideal gas, we want to have low pressure, lots and lots of room for molecules to run around, and high temperature, lots of energy. That way when they collide with each other, they don't stick. All right. So when we look at nitrogen, here's the same gas now. It's nitrogen for all 3 at 3 different temperatures. And so we can see that idea that as we increase temperature, it becomes closer and closer to the ideal. So again, we want pressure to be low, temperature to be high, because the energy will be high. And when it's high, that means that when the things collide, they're not going to stick together or repel as much. They don't touch each other long enough to interact. Okay? So don't get scared of this. I'm just showing you this because many of our students in this class are engineers. This is the real ideal gas equation. It accounts for those problems we were talking about. Okay, so the attractive and repulsive forces are accounted for with this A term, we call it. This is a fudge factor. This is a way of accounting for attraction or repulsion, and it's going to depend on the substance. So you just look up the value and plug it in when you need it. This is why engineers are famous for using tables, okay? So this is one of the tables that you'll be using when you work with gases. The volume of an atom thing is accounted for here in this B term. So, it's dependent on how big the particle size is, basically. All right? I don't want you to memorize this. We're not even going to do any examples. I just wanted to make you aware of it because it's going to come up in your future classes. All right? These are called van der Waals constants, by the way. That has to do with what we call intermolecular forces. All right, so now what you need to do is go on Blackboard and take the online quiz. You can take it as many times as you like prior to our deadline, and that's how you're going to get credit for doing this chapter, along with bringing in your notes so I can look at them next Wednesday. As usual, if you have questions, please do email them to me, preferably before Wednesday so we can talk about them in class, or you can ask me the questions in class.